again, and this is probably the last video I'll make this year. So welcome to the video going over this question. So whenever you're doing any type of cell, galvanic cell, or the cell that I showed you today, where they apply an electric current, you always have to flip one of the half reactions because one has to be an oxidation and the other one has to be a reduction. So here they're not applying any current, like you don't see that there's no external power source. So here you have to flip the one that will make the E0, positive. So in order to do that, we need to flip this reaction. So you'll see that, so you should write this reaction flipped, which I did, you'll see at the bottom. And then we also need to balance it. Notice that the electrons are not balanced. So everything in this equation by 3. So this is going to become 3, this is going to be 12, this is going to be 12, and this is going to be 6. So for this for A, so I wrote these reactions, pre-wrote them to save some time. So again, we're going to add them. Notice that I flipped and did the multiplication, and we'll notice that what happens is that the hydrogens and electrons cancel. And what's left is our alcohol plus 3 waters plus 3 oxygens produces 2 carbon dioxides and 6 waters on this side. And if you notice now, there's excess water on this section is this. These waters end up canceling. So the final reaction is this. And there are 3 waters left over. Because again, there was I didn't see the waters on both sides, but there's 3 excess waters on the reactant side. And if you look, you see that balances. On this side, there are 6 hydrogens. On this side, there are 6 hydrogens. 7 oxygens there. Everything seems to be balanced. So that's the first one. That's A. And then all we have to do for B is we have to add these values, okay, with that one being positive. We just add the E0 values with the one that we flipped the sign. So E0 is equal to 1.29 plus the one we flipped, which was I can't read my own handwriting, 0.85, and that is 1.314 volts. Alright, so that's for A and B. And now for C, it says a 10 milliliter sample of that's ethyl alcohol is put in an electrochemical cell. The cell produces an average current of 10 amps for 20 seconds, at which point the ethyl alcohol has been totally consumed. Calculate the charge in coulombs that has passed through the cell. Well, today I showed you the new last final equation that we needed to, where current is Q over T. Alright, and they gave us the current. If you look back up, they said that the current that was applied was 10 amps. And it was applied over 20 seconds. So our Q, or the total coulombs, is 2 coulombs, or 2C is the abbreviation there. That's just applying that new formula that we learned. Okay, now this is the harder part. Okay, it says calculate the initial ethyl alcohol. I'm sorry, this is ethyl alcohol. So mean that and that formula mean the same thing in the solution. Okay, so we want to we know that 2 coulombs of charge ran through this cell. So we're going to put that over 1. We need to find out how many electrons that is. So we know that there are 9 from the formula sheet. There are 96,485 coulombs in 1 mole of electrons. So that's converting to 1 mole of electrons. Now in this cell, there were 12 moles of electrons, and we know that from up here, we canceled out the 12 moles of electrons per 1 mole of the alcohol, the C2H5OH. And if you do this math, so again, we're converting from coulombs, the amount of coulombs, to the moles of electrons, to the moles of ethyl alcohol. And if we do that, that gives us 1.7 times 10 to the -6 moles of the alcohol. And they want, so that's the moles, and they want the molarity, and we know molarity is moles over liters. So we can take this number here, that's the moles, and after the thing would go away, and divide it by, they said that it was 10 milliliters. If you look up here, it said 10 milliliters right here. So we divide that by 0.01 liters, and we end up getting, and I think if I sig fig correctly, 7.1 times 10 to the negative 4 m for D. All right, so now the rest of the problem is not a electrochemical cell. This is actually Beer's law, and there are two ways to do D. So it says calculate the value. So we want us to calculate the value of this, the concentration of this at 1.5 minutes, and again, this is orange. And it's going to get less orange. As this reaction occurs, it's going to become blue-green. And they give us the initial concentration and its absorbance. So one of the easier ways, so one way you can do this is take this equation, okay, and then solve for the constant, which is A, and then redo the equation. Because you have, for the initial, you have the molarity, you have the path length, and you have the absorbance of the initial. So you can solve for the absorptivity constant. The other way is to do a proportion. So we know, and I'm going to show you that way because most of you didn't do that way in class. So we know the absorbance and concentration of one, that's proportional to the absorbance and concentration of another. So we know that the initial absorbance was 0.782. And the concentration of that, if we scroll up, they tell us originally was here, 1.0 times 10 to the negative 3. And now they want us to find the concentration at 1.5 minutes. So we have the absorbance, which goes on top, 1.553, and then we can cross multiply and just get the concentration. I'm sorry, and up here I was wrong. I wrote the wrong number for my math. This is 1.7 times 10 to the negative 4. I'm looking at the wrong circled answer. My bad. Can't do math. Anyway, let me do the cross multiplication. So 1 second e to the negative 3 times 0.553. Divide that by 0.783. And then put it in scientific notation. And we get 7.1 times 10 to the negative 4 m. Alright. And again, I'm sorry about this up here. I read the wrong number, even though I had done the math already. And then for E, the student runs the second trial, but this time uses a curvette that has a path length of 1. So it was 0.5, and you're doubling the path length. Describe how the experimental setup should be adjusted to keep the initial absorbance at 0.785. Justify your answer with respect to the factors that influence the absorbance of the sample in the spectrophotometer. So this is E. So if you remember the equation, E for Beer's law. So absorbance is equal to the absorptivity constant times B times C. So you're doubling this. So the only way to keep the absorbance the same is to half the concentration of the C2H5OH minus 2. That's what you're measuring the absorbance of. Because if you double this, you can't change the constant. So if you want to keep the absorbance the same, if you double the path length, you have to half the concentration of the thing that you're measuring. And then last but not least, F, which is a kinetics question. So for the concentration of reactants used in the experiment, the rate of the reaction can be written as follows. Explain how the experimental data indicates that the reaction is first order with respect to Cr2O7 minus 2. So there are no lines or graphs here, so the only way to tell something is first order is to look at the half-life. And if you remember, the half-life is constant. So let's see if there's any place when an absorption is like equal to saying like moles here, because the absorption measures the concentration. So if you look at here, this is about halving. So if you multiply this by 2, you get about that. And that takes 3 minutes. So let's take half of this. Let's do 0.389 and take half of that and see if it's close to that. And I'm in scientific notation, which is 0.945, which is really close to that. And notice 3 minutes has also passed. So this, because the half-life is constant, and you'd have to, when you were writing this out, you'd have to explain and show. But since the half-life stays constant at 3 minutes, the reaction is first order. Alright. Stays, I can't write. Half-life. Alright. And again, when you were doing this, you would explain, that, you know, from 0 to 3, the absorbance halves, and that's just like halving the moles, because it's the moles that are causing the increase in absorbance. And then from 3 to 6, which is also 3 minutes, the absorbance halves again. And since the half-life is constant, the reaction is first order. Alright, make sure you hand this in. Have a good day.